Section 4.4 is curve sketching, and all this really is a sort of a comprehensive review of the skills from algebra up through what we've learned in calculus so far, and an application of a set of those skills to sketch the graph of a function or to sketch the curve associated with a function. So you'll notice that most of this stuff is actually not calculus, right? The guidelines for curve sketching are generally the steps that you'll take or the information that you'll need to find. Are these A through H steps that we have below. I believe that's 8 steps total. And first is the domain of a function. That's an algebra question. The intercepts, the x and y intercepts of a function, that's essentially algebra again. The symmetry of a function, whether or not the function's even, odd, periodic, or none of the above. Asymptotes, horizontal and vertical. Vertical asymptotes we're able to find through algebraic means. We're looking for places where the denominator is 0. Horizontal asymptotes we'll find by taking the limit as x approaches positive infinity and then as x approaches negative infinity. So those are our two cases for asymptotes. Intervals of increase or decrease. That's calculus, right? We're looking for places where the first derivative is positive or negative. Those are intervals where the derivative is positive or negative. Those will be between critical points, the places where the derivative of the function is 0. Local maximum and local minimum values. Remember, we can find these by looking at intervals where the function changes from increasing to decreasing or vice versa. That was from the previous section. Concavity and inflection points of the function. That involves the second derivative. In order to talk about concavity of the function, we set the second derivative equal to 0. We solve for x there, and then we use test values on either side of those zeros for the second derivative to see whether or not we're concave up or concave down. Remember, the second derivative being positive for an interval means we're concave up. It being negative means we're concave down. Inflection points are points where concavity changes from up to down or vice versa. Lastly, with all 7 of these pieces of information lined up and laid out, we can sketch a graph of the curve. One other thing I should mention as well, if we have a critical point for this function, f prime of x is equal to 0, and then we know that the function is concave up or concave down, and that at that point, then that's another way to know whether or not you have a local min or a local max. So hopefully we'll see that in the examples to come here. So we're going to use these guidelines to sketch the graph of y equals x to the 4th minus 4x. Now, of course, this is a polynomial. There are a few things we could do with this algebraically. We expect some stuff about it. Positive x to an even root. Its finishing behavior looks like this. In behavior is this, right? Finishing up in both cases because it's even and has a positive coefficient. But we can do better than that because we know quite a bit more stuff about these functions now, thanks to all the calculus we've been doing. So let's get into it. The domain of this function, well, it's polynomial. Its domain is all reals. We handle that. Let's see. The domain sometimes can help us with the vertical asymptotes, right? If we throw out any values due to division by 0, then we're going to check those values as asymptotes later on, probably. Also, another thing that we know is if the domain is all reals, then there won't be any vertical asymptotes, right? There might be horizontal, but there won't be vertical. So that's good to realize. Okay, so the intercepts of this function. Well, for the x-intercept, that's when y is equal to 0. So we set the function itself equal to 0 and solve for x. X-intercepts are x values, right? So setting this function equal to 0 results in this once we factor on the left-hand side. First solution to this is x equals 0, and then the other side is x cubed minus 4 is 0. That's x cubed equals 4, and that's x equals the cube root of 4. And we'll just leave it as that. Cube root 4 is perfectly sufficient. And so we've got two x-intercepts when x is 0 and when x is the cube root of 4. Second, the y-intercepts. This is a little easier. The y-intercepts is when we just set x equal to 0. When x is 0, that's when we're on the y-axis. So when x is 0, we just plug in a 0 to our function everywhere there's an x, and we get, well, 0 to the 4th minus 4 times 0 is 0. So our y-intercept is y equals 0. Cool. And we know that, of course, for each of these pairs of points, so if the x-intercept is 0, that's the place where y is 0. In other words, we cross the x-axis, and one place we cross the x-axis is at x equals 0. The other place we cross the x-axis is at cube root of 4. So the other point on this curve is cube root of 4, comma 0. It's nice to keep in mind. This coincides with this. Okay, also, now moving on to symmetry. Is this function symmetric? Well, how do we check that? We, if this is y of x, right, our function some y value based on x, then we write down what our original function is, and then we plug in negative x to our function's argument. So everywhere there's an x, I put parentheses, negative x, and then I simplify the expression. Here, negative x to the fourth is going to give me positive x to the fourth. Then I have minus 4 times negative x. Well, that's plus 4x. So this function, the result after simplifying, is not equal to the original function. So this function is not even. The last thing to check is this. Negate the whole function here. So multiply by a minus sign in front of all of these. And we have negative x to the fourth plus x to the fourth. This one is not equal to this one either. So again, we compare these two, and we compare these two. These two aren't equal because of the minus sign in front of x to the fourth down here. So the function's not odd either. Also, in terms of periodicity, well, this is a polynomial. It's not periodic. I think sine and cosine, tangent, it's when we're dealing with trig functions that we might want to consider whether or not a function is periodic. So in this case, we just answered neither. It has no symmetry. Now, moving on. Asymptotes. We've already seen there won't be any vertical asymptotes because the function is defined everywhere. It's a polynomial. So that's good to rule out. Let's see. Next up, horizontal asymptotes. When we take the limit as x approaches negative infinity of the function, same for positive infinity. In both cases, we appear to get positive infinity. Well, that fits our algebra notion of upward in behavior on either end. So there we have that. So that matches. We don't have any horizontal asymptotes because that's not a, these limits diverge, right? They diverge to infinity. So there's nothing that we're approaching. It's just infinity. Intervals of increase or decrease. In order to find this, we need the first derivative of the function. So y prime of x to the fourth minus 4x is 4x cubed minus 4. The derivative of our original function is 4x cubed minus 4. So the critical points, we set the derivative equal to 0, solve for x. Well, divide both sides by 4, and I get x cubed minus 1 equals 0. So x cubed equals 1. And when we factor this, well, we see immediately one solution looking at it. Well, x cubed equals 1, and then solve for x, that's cube root of 1 on the right-hand side, so x equals 1. Another way to do it is we might factor this thing out as follows. See that x equals 1 is a root here, and we could convince ourselves that this quadratic term does not have any real roots. So we don't find any more real roots than we did going this route. Either way, that's fine, as long as we arrive at the same conclusion. And either of these paths will arrive at the same place so long as you do them both either correctly. So we only have one critical point. So we're going to place that on a number line. Now I need a test value to the left of 1. Why not 0? I need a test value to the right of 1. I'll use 2. Y prime of 0, I'm plugging 0 into this number. It's 4 times 0 minus 4. I get negative 4. Negative 4 is less than 0. So we're decreasing on this interval. As for my test value of 2, y prime of 2, I plug 2 into this function. 4 times 2 cubed is 4 times 8. 32 minus 4 is, well, whatever it is, it's positive. That's all that really matters to me. So I must be increasing on this interval. That's it. We're decreasing on all of the interval on the left, and we're increasing on all of the interval on the right. The reason we know that is because there are no more critical points. There was only one critical point for this function. If it's going to change decreasing from decreasing over here somewhere, it would need another critical point somewhere on the number line. It doesn't have it, so this behavior is fully determined as we see it here. Okay, maybe another thing I can add with this increasing decreasing situation is maybe an arrow here and then an arrow here. And what this helps me think about is concavity, which is coming up. We haven't determined it yet with the second derivative, but it looks like this function is probably concave up. So that's a good thing to keep in mind. Also, since the function switches from decreasing to increasing, this is one thing we do know. This critical point of 1 or critical number of 1 is a local minimum, right? It's the bottom of a descent and it's the beginning of an ascent as we move from left to right. So it looks like we have a local minimum and this function's concave up for, well, a good bit of it. We don't know that for sure, but it's a little hint, right? And it looks like quite possibly this will be the case. So let's see. To write down our intervals of decrease, remember we're decreasing everywhere to the left of -1, or of +1 rather, that critical point, and we're increasing everywhere to the right. So there we have it. Moving on, local max, local min. Well, we already declared this. We knew that we had a local min because we switched from decreasing to increasing. Well, the local min occurs at the value of x equals 1. What's the y value of this local minimum, or what is the local minimum? Well, you take this 1 and plug it back into the original function, x to the 4th minus 4x, or 1 to the 4th minus 4 times 1. I have 1 minus 4 is -3, so the point where my local minimum occurs is the point 1, -3 on the coordinate axes. So that's going to be one known point we can plot, and we should always try to plot our local mins and local maxes explicitly. Now, there was nowhere where the graph changed from increasing to decreasing, or where the function changed from increasing to decreasing. So there's no local maximum. There's no top of a local hill anywhere. Concavity and inflection points. Now we're at the second derivative. The second derivative of 4x cubed minus 4 is, well, the first derivative was what? 12x. Actually, let me go back. Sorry. Go to here. Oh, sorry. The first derivative was 4x cubed minus 4. The second derivative is 12x squared. Check that on your own to make sure you get the same. We have 12x squared as our second derivative. And just as we did with the first derivative, we set it equal to 0. And we solve for the x values. They're not critical numbers, but these are the zeros of the second derivative. Talk about what they'll tell us in just a moment. 12x squared equals 0. The solution to that is x equals 0. Divide both sides by 12, take square root of both sides, x equals 0. So at x equals 0, we want to check either side. Are we concave up, concave down? What's going on either side of this x equals 0? We're not positive or negative here at x equals 0 because that's where the derivative was 0. Second derivative was 0. So try a test value of -1 on the left, test value of 1 on the right, and we'll see what's going on with this function. Y double prime of -1, well, we plug in -1 to 12x squared, and we get 12 times 1. That's positive 12. So we're concave up on this interval. Similarly, for x equals 1, y double prime of 1 is 12 times 1, which is greater than 0. We're concave up once again. So it looks like we're concave up in both cases. And now we check along these intervals, concave up and then concave up. This point 0 was a place where potentially we switch concavity. Since we didn't switch concave up to concave down or vice versa, we don't have any inflection points. We have no inflection points because concavity of this function does not change. So don't automatically declare the 0 of a second derivative to be an inflection point. It may or may not be. In this case, it's not. So we want to keep that in mind. It's a candidate to see whether or not it's an inflection point, but if our concavity doesn't change, well, then it's not an inflection point. So let's put all of this together. Oh, let's note one more thing I was pointing out. This was our critical point at x equals 1 for our first derivative, right? Our critical number. Notice that it's concave up here. Well, that means whatever was going on, that critical point where we had a horizontal tangent line, right? Concave up, this is a local minimum, right? As we determined above already. So that's nice that the second derivative can help us sort of support that situation. We happen to use the exact correct test value to find that out. 1 was our critical number from the first derivative. And if we plugged it into the second derivative and saw that we were concave up, we can know automatically that this must be a local minimum here at x equals 1. So that's just a redundant bit of work we could do, or just a nice check for these problems. Okay, let's put it all together. I know that I have a local minimum at 1, -3, so I'm going to plot that point. Any points that I bothered to find here, I should do the work of finding them. So 1, -3 is here on the graph. That's my local minimum. Okay, so 1, -3, I'll just label it local min. I know my finishing behavior is up and right and up and left, right? Left and up, right and up. So that's good. We can get to that when we draw it. Now let's see what else I can fill in. What other points do we know? We don't have any local maxes, so that's not worth anything. Let's see, we don't have any inflection points, so we don't really need to mark that out because concavity never changed. We're concave up everywhere. Let's go back, see real quick. Oh, our intercepts, right? Looks like we have an intercept at the origin, 0, 0. We have another x-intercept at cube root of 4. Cube root of 4 is, maybe we'll say that's approximately 1 1/3 or something like that, right? I'm just taking a really rough guess, 1.3 or something. You might plug that into a calculator to get a better idea of what that actually is. So yeah, let's get to, maybe it's 1.4-ish, something like that. 1.3, 1.4. Doesn't matter. We're gonna sketch it. So 1 point at the origin. And anything else we need to do? Well, we know that we're decreasing on the left of 1, increasing on the right of 1, concave up the whole time. And let's see what else. I think we have no asymptotes. We have no symmetry. So, okay, well, let's plot those other 2 points and get this thing graphed. Let's see, 0, 0. Whoops, point on the origin here. So here's that. It's one of our x-intercepts. And then I said something like 1.3 or 1.4 is this other intercept here. It's going to be pretty narrow and close to itself, but we can see that the symmetry really is kind of ruined, right? This will not be a symmetric looking curve because it's not centered around this local min or local max, or sorry, this local minimum right here. Okay, so let's see if I can draw this reasonably well. Or maybe not. Let's see. Kind of a hard function to draw. I didn't do it much justice, but because it looks like we actually have an inflection point, which we really shouldn't, right? It should always be concave up. It looks a little concave down right here. Nonetheless, it's just a drawing on a tablet here. It makes it a little more difficult. So there we have it. We draw this to the best of our ability. Notice one thing I don't do. I didn't add a flourish here, like a little tail that flattens out, because that would make it concave down, right? I could have extended this curve to do that, but I'd switch to concave down. I'm sort of honoring this information by not doing that. And this is my little kind of erroneous spot of this just due to poor drawing. It wasn't meant to be concave down there. So maybe I'd really want to fix it and draw it a little better here. Let me try one more time to get that correct. Point here. See if I can just keep getting this little kink in it. There we go, something like that. Okay, almost looks right. So good. But we've got the gist of it, right? We can use this information to graph these curves. So the finishing behavior, as x approaches infinity, y is going to approach infinity. As x approaches negative infinity, y is going to approach positive infinity. So there we go with our end behavior, to reiterate that. Let's see another one. We'll walk through all these steps again, and I have a better drawn graph at the end of this, so we can see maybe a nicer version of it. So the domain of this function, well, remember we need to eliminate any places where we might divide by 0, right? Or have a division by 0. So that's when the denominator x squared minus 9 is equal to 0. Solve this equation, you get x is plus or minus 3. So we need to delete negative and positive 3 from the real number line. So the domain of this function is this. Negative infinity to negative 3, negative 3 to 3, 3 to infinity, not including any of those endpoints. And we've effectively punched out negative 3 and 3 from the number line. We're going to have a heads up for potential vertical asymptotes here at x equals negative 3 and x equals 3. We'll check on that in a moment. We move on to intercepts. The y-intercept is when x is 0. That's the easy one. We just plug in 0 to this. Well, the output is 0. When we're looking for the y-intercept, the x-intercept, that's when y is 0. So that's when the function itself is equal to 0. When we solve for this, well, this amounts to x being 0. Right? Remember, we multiply both sides by x squared minus 9. We have x equals 0 is what remains. And of course, we see that the origin in both cases provides our intercepts. So this function, this curve, passes through the origin. We could have seen that pretty quickly by plugging in 0 for x up here and noting we get 0 out. Symmetry. Is this function symmetric? Well, y of x, we write down a copy of it, then we do y of negative x. Everywhere there's an x in here, I put in negative x, and I see what I get out, right? I simplify this. So I have a negative x in here, it's going to square and be a positive x squared minus 9. This function is not equal to this one, so these two aren't equal. So this function does not have even symmetry. Now I check the last version where I take my original function and multiply it by negative, and I get negative x over x squared minus 9. Well, that's negative x over x squared minus 9. This matches, so the function is odd. The function's odd, it has symmetry about the origin. Remember, that's rotational symmetry by 180 degrees. We'll talk about that when we go to graph this thing. Asymptotes, we've already had a heads up. X minus 3 and x equals negative 3 and x equals positive 3 were potential asymptotes. What you'd want to check is what's the limit as x approaches 3 or x approaches negative 3, and you'd see that, yes, of course, that's a positive or negative infinity. It's probably important to actually see which one's which, right? So maybe we do that real quick. The limit as x approaches, let's see, 3 from maybe the left, positive 3 from the left of x over x squared minus 9. Is this positive or negative infinity? We'll have to determine this. 3 from the left, positive 3, that's 2.99. Those are numbers that are slightly smaller than 9, right? So we're going to have like 8.9, 8.9 and minus 9. We're going to have negative 0.0 something. 3 over that negative. And this is eventually going to be going to 0 in the denominator. So we're going to go towards negative infinity in this case. That's good to know. In other words, does the function go up or does it go down when it runs into 3? Right? On the left side, it goes downward. If we approach 3 from the right, what happens? X over x squared minus 9. Those are values like 3.1. They're bigger than 9. It's positive. We're approaching 0 in the denominator from the positive side. So we're going to run to positive infinity. So that's good to know. You can do the same check for negative 3 from the left and from the right, and you'll see that it's opposite this, because negative 3 approaching it on the left, you'd be approaching it from negative 3.1, negative 3.01. If you're approaching it on the right, it's negative 2.9, negative 2.99, that sort of thing. So anyway, there are other ways to get at this, but it's good to have this little bit of information here to help us with the sketch, just in case. The horizontal asymptote, let's move on to that. That's the limit when x approaches negative infinity of the function and when x approaches positive infinity. Function can have as many as 2 different horizontal asymptotes, one to the left and one to the right. Can have as few as none. Now, what is the limit as x approaches negative infinity of this function? Well, it looks like I've taken the lead term from my denominator, which is x squared, and I'm dividing both the numerator and the denominator by it. That's this expression here. And I end up with 1 over x in the numerator over 1 minus 9 over x squared. What does this go to? The numerator goes to 0 as x goes to infinity. The denominator goes to 1 minus 0 as x goes to infinity. So we have 0 over 1 minus 0, or 0 over 1, and that's well defined as 0. So as we approach negative infinity, the function approaches 0. We have a horizontal asymptote of y equals 0 on the left. On the right, we do the same work, and we'll see that it also 0. So we have a horizontal asymptote of 0 on the left and on the right. Moving on. Intervals of increase or decrease. So we need the first derivative of this function. In order to find the first derivative of our rational function, we have to use the quotient rule. Quotient rule. So here's an implementation of the quotient rule. We've got simplifying the numerator, or multiplying those terms out, got the following, and then we end up with this overall simplification of the quotient rule. It looks like we have negative x squared minus 9. Be careful, we're tempted to cancel that possibly, but notice that they're not in common, right? If we factor the minus sign away from each of these, this is actually an x squared plus 9, not x squared minus 9. So we don't get any cancellations here, but remember we're looking for critical points, so we know where to do our test values for increasing or decreasing. So we want to know when this function is equal to 0, when the derivative is equal to 0. Okay, well, where's the work for that? Is that done anywhere in here? Oh yeah, here it is. When the derivative is equal to 0, well, the denominator can never make this expression equal to 0. The only thing we have to dodge is whether or not, I guess we have to think about whether or not we have undefined values. But what we're looking for here, let me just take this one step at a time. Let's determine whether or not this function can be 0 for critical points. Well, the only way it can be 0 is if the numerator is 0. So let's work on that. Here's the numerator equal to 0. Negative x squared minus 9 equals 0. Well, add x squared to both sides and we get x squared equals negative 9. There's no real number that satisfies this equation. So there is no 0 for this derivative. It does not have a real root. Okay. Now we're not done though. We want to take some care here and remember something else. X equals plus or minus 3. That's where this denominator of this derivative could be 0. Remember, critical points are also the points where the function is undefined, where the derivative is undefined. That comes from solving x squared minus 9 equals 0. That has a solution. X squared equals 9, and x is equal to plus or minus 3 in that case. So here's our undefined critical points, right? Plus or minus 3 are the points that make the derivative undefined, or the points at which the derivative is undefined. Here they are in a number line. I need to put a test value. Negative 4 is left, 0 is in between, and 4 is to the right. And I want to check all of these. So I need to plug negative 4, 0, and 4 into this function. And let's see, we did y of negative 4 here, or y prime of negative 4, and it looks like we got something less than 0. Right? We're doing it, this is the negative number we get out up here over a positive number. So negative over positive is negative. And we can see probably if we do 0, well, 0 is easy. Plug in 0 to this, our other test value, and we get a negative 9 over negative 9 squared. So this is a positive number on the bottom. A negative over a positive is also less than 0. So far, we're negative in the derivative here, so we're decreasing. Negative in the derivative here, so we're decreasing. And the third one, looks like y prime of 4 is also negative, so we're decreasing again. How do I know that? Well, plug in a 4 to this. It's no different than when we plugged in a negative 4. We're still going to be less than 0. So in all three cases, we're decreasing, which is interesting. None of these critical points should be local min or local maxes then. So we'll have to keep that in mind. So it looks like the function decreases everywhere. So we're not increasing anywhere. So increasing is the empty set, and we decrease on all real numbers. There we have that. Now, final steps here. Local max or local min. We didn't change decreasing or increasing, so we don't have a local max or a local min. That should also, Well, it's going to be interesting. We're going to see how this connects to concavity, and that'll be a curious thing that I was hinting at earlier. So if we have y prime as this function, we need the second derivative of this function. Well, here's the quotient rule applied to this function. Here's the first steps. There are some nice cancellations that come out. Here I start to group terms or simplify at least from the cancellations. Here I group like terms after multiplying these out. And ultimately I end up at this simplified version. What are we interested in? We want to know when the second derivative is 0, just like with the first derivative. Well, that's effectively solving the numerator of the second derivative being equal to 0. And we can see that we can factor a 2 out, or divide 2 on both sides. We can factor an x out of this expression, and we arrive at this. So we have 2 possible solutions, maybe even 3 here, actually. We have x equals 0 as a solution. The other one is x squared plus 27. So it looks like x is equal to plus, or, oh, actually that doesn't have a solution, right? X squared plus 27. If we try to solve for it, we have x squared equals, so x squared plus 27 equals 0. X squared equals negative 27 is our first step to solve for that, and there's no real number that satisfies that. So we only have 1, 0 for the second derivative, and that's when x is 0. So we want our concave up and concave down scenarios, right? Oh, there's another thing we need to check, and we'll get to that in just a moment. So here's x equals 0. The other thing we need to worry about is this. I glossed over this. The undefined portions of the second derivative. The undefined portions of the second derivative, well, it's when the denominator is 0 here. That's when x is 3 or negative 3. So we have 3 critical points, negative 3, 0, 3. Sorry, we have 3 zeros of the second derivative. They're not critical points. They're just zeros of the second derivative. They're candidates for inflection points. So what do we need to do? We need to plug in test values on all sides and in between all of our zeros of our second derivative. So to the left of negative 3 is negative 4. Plug that into our second derivative. It looks like we get something negative, right? We're claiming that. You could work out the details. Remember that we're just plugging it into this function, but you'll see that we get a negative number out, so we're concave down on this interval. We plug in negative 1. Y double prime of negative 1 looks like that turned out to be positive. You might need to confirm these details on your own, but nonetheless, comes out to be positive, so we're concave up in that interval. Now our next test value is 1 between 0 and 3. Plug in 1, looks like we got something less than 0. Again, you can confirm that on your own, and we get concave down for that. And then lastly, when we plug in y double prime of 4, looks like the evaluation comes out to greater than 0, so we're concave up. So we do have inflection points, right? We're concave down, then up, then down, then up. So we have an inflection point of negative 3, 0, and 3. Every one of our zeros of our second derivative turned out to be inflection points. So we'll note that when we go to graph this curve. Okay, we had no local min or local maxes, and we had some vertical asymptotes. So I recommend that be the first place we start. We had a vertical asymptote of x equals negative 3. We had one for x equals 3. If you go back to the previous page, you'll see that. So we have those sketched in. Moreover, we did ourselves a favor back here. We said we determined the behavior as we approached positive 3 from either side, from the right and from the left. If we approach 3 from the right, we're trending towards positive infinity. If we approach from the left, we're trending towards negative infinity. What that tells me is the following. It tells me 3 from the left, we were negative. Right? 3 from the right, we were positive. Right? Is that what we have back here? Yep, exactly. 3 from the right, positive, 3 from the left, negative. So I could sketch just this portion, these portions of the curve that I've highlighted right here, and be fairly confident in it. If I had done the same work over here, I could do the same and just know that, okay, this little branch of these curves, and I'll finish drawing what's not highlighted once I'm sure what's going on. Well, the horizontal asymptote tells me something as well. If I'm up here then I know that this curve is going to approach 0 as we go to positive infinity. This one's going to approach 0 as we go to positive infinity. One thing I might want to know is, well, if I have these behaviors, right, without thinking about the horizontal asymptote at the current moment, I could also consider whether or not, or what my symmetry is, right? I see that these two things are, this section and this section are kind of lining up. If I rotate 180 degrees, then these are going to match up and be as is. So my asymptotic behavior looks correct. Maybe I didn't need to do the limits as we approach -3 from the left or from the right, because I know that odd symmetry is going to force this section to be to rotate onto that section and cause and dictate what that one looks like. Okay, so what's a point that I know that was on this graph? Well, I know that its intercept was here, so I could place that. I know the function's always decreasing. That's another interesting thing, right? It's decreasing everywhere. So I expect all of these curves to be decreasing, and they are, the way it's drawn. So we've been able to capture that. Do I know any other points on this? Not really, but what I might be able to say is this. From concavity, so I have a couple choices. I could either use a test value on the left end and the right end, or I could just use concavity to tell me everything else I need to know about this thing. It's concave down to the left of -3. I know that the limit this way, we have a vertical asymptote, we're pointing downward here. And I know we have a horizontal asymptote, we're pointing out to the left like this. Is there any other way I could draw this? Not really, right? If I didn't do those limits to know that I was pointing downward, and if I didn't use symmetry to help dictate that, then I would just know that thanks to being concave down, there's no way this thing could be in this format, right? Because that's concave up. So it's a lot of redundant information that helps me check this out. It's concave down, horizontal asymptote of 1, vertical asymptote of -3. It's decreasing, right? Also, this one is not decreasing, so that's not an option either. Here, I know this point, and maybe I check both sides of this, but I can also use symmetry. I've already checked this, so I know that as we approach, whatever this curve looks like, it's going to connect to here now. It'll rotate and match up to that, so I could sketch in this dotted version of it on the left. And that's thanks to the symmetry of this thing. It's got odd symmetry. And then look, concave up, and that checks out here. Concave down, and that checks out here. Okay, there might be some drawing and erasing of these things, right? In WebAssign, when you're given a choice of graphs to pick, then you can just use deductive reasoning, right? And just figure it out from what properties you expect and which curves that you have as a choice satisfy that or don't. So there we go. There's this is a kind of a big and messy process, but there's nothing terribly difficult about it. You follow the same steps every time, so that should be reassuring. Let's do one more. Use the guidelines of this section to sketch the curve y equals x tangent x, just on the fixed interval -pi/2, pi/2. I wanted to make this a little bit easier to manage and not do all real numbers. Okay, so the domain, well, we're restricted to -pi/2 and pi/2, which is a good thing because tangent of x is not defined outside of this, right? Or not, well, it's not defined at pi/2. Maybe we'll investigate its behavior there because we do recall that it's asymptotic. So intercepts, the y-intercept, that's when x is 0. Well, that's y is going to be 0, right? When x is 0, we plug a 0 for x in, and we get 0 out for y. When to find the x-intercepts, we plug in y equals 0, or we try to solve this equation. Well, this equation is 0 whenever x is 0, or whenever tangent of x is 0. Well, tangent of x is 0 when x is 0. There are other solutions to that, but none of those solutions are in this interval, so we don't have to deal with those. Okay, the symmetry of this curve. Well, y of x is x tangent of x. Now we have to remember some interesting facts. Y of -x is -x times tangent of -x. So then I have Remember what tangent of negative x is as an even or odd function. It's odd. So what it does is it passes out this minus sign right here. And it lets it pass out as negative tangent x and has the property of an odd function. So then I have a negative times a negative, and I end up with positive x tangent of x. Well, that's equal to my original function. Y of x equals y of negative x. So I have even symmetry. I have folding symmetry about the y-axis, right? Or vertical symmetry. So that's a nice tool we've already seen to be able to exploit symmetry to inform us on how to sketch the graph of something. Asymptotes. The vertical asymptotes of this function are here and here. Now, sure, they're not in the interval technically, but they're the boundaries of the interval. So we want to keep those in mind. As we approach negative pi over 2 from the right, so those are, right, we're coming this way at negative pi over 2. Well, tangent is approaching negative pi over 2, or negative infinity, and x is approaching negative pi over 2. So a negative times a negative gives us a positive, and that's how we're approaching positive infinity. If we weren't sure about that one, then we could approach positive pi over 2 from the left and realize that, well, that's going to a positive number, and these numbers are getting arbitrarily large and positive, so we have a positive infinity here. So that being the case, if I knew this side, this is on the other side of negative pi over 2, and since it's symmetric, I know that if I'm up towards infinity on the right-hand side for this one, then over here at pi over 2 on the left-hand side, I know that I must be upward too. It has symmetry about this vertical line at the origin. So that helps us work that out. All right. Horizontal asymptotes. Well, what's the limit as x approaches infinity? Well, as x approaches infinity, well, tangent of x, it's more or less undefined because it's got a bunch of asymptotes in it, but it's really outside of our interval, right? We can't have a horizontal asymptote because we can't approach infinity. We can't leave the interval negative pi over 2 and pi over 2. So there aren't going to be horizontal asymptotes when we're talking about a fixed interval. So that's a foregone conclusion. Intervals of increase or decrease. This is where we need to take the first derivative, set it equal to 0. Here's that work. Okay, tangent x plus x secant squared x equals 0. I've used the product rule. And let's see, I'm trying to work on this a little bit more. What did I do to get from here to here? Well, it looks like we multiplied both sides by cosine squared x. What did that leave? That canceled a cosine x underneath sine x here in tangent. So I get sine x cosine x, and it cancels secant squared x altogether. So I have sine x cosine x plus x equals 0. I think that's an easier thing to solve than otherwise, right? Let's get it all in terms of sines and cosines potentially, because those are just functions that we know a little bit better from trig. When is this 0? Well, guess and check is really the only tool we have for this. Well, when x is 0, that's one place it's 0, right? That's good to know. So that's our one main critical point, right? When x is 0. Now, is x equals 0 in our interval? No, yes, it is. So that's fine. Do we have anything else in our interval that might do it? You might want to convince yourself, guess and check. That's really just kind of the best tool we have available here. Guess and check at some values that might also make this thing negative, right? So, pi over 4, pi over 3, special angles, things like that. I think you'll convince yourself pretty quickly that the only way for this thing to be 0, right, is for x to be pi over 2 or 0, right? And if any of these values are equal to x, if we use special angles, if x is pi over 4 or pi over 3 or something, well, we don't get out a pi over 4 or pi over 3 here. We get some radical value out, and that's not equal to that x over here. So anyway, you kind of have to convince yourself that this only has the 1, 0. And nonetheless, we move on to the number line. We set our critical point on the number line, We know that we're going to stop at negative pi over 2 and at pi over 2 going left or to the right. So we need test values within those intervals. Negative pi over 4 and pi over 4 are perfectly appropriate for that job. Y prime of negative pi over 4 is, well, it's either this function or we can go back to the original, this one, right? What we found for y prime. Plug it in and see what we get. We only care if it's positive or negative. It looks like we get through all this work, it's going to be negative. Convince yourself that this expression here is actually negative. Why that would be the case. Remember, we have cosine squared of something. It doesn't matter what that something is as long as it's not 0, which it's not. It's going to be positive, and this is negative minus something times a positive. So that's all negative. So we know we're less than 0. So we know we're decreasing along this interval from negative pi over 2 to 0. Do the same thing for positive pi over 4. Y prime of positive pi over 4, you'll see you get a positive number out, so we know we're increasing here. So something else we know is we have a local minimum. We have a local minimum at x equals 0 because we switch from decreasing to increasing. Intervals of decrease, negative pi over 2 to 0, not including the endpoints. Increase, 0 to pi over 2, not including the endpoints. Local max, there are none. We don't switch from increasing to decreasing anywhere. Local min, there's one. At x equals 0, we switch from decreasing to increasing. So we form a local minimum. What is that local minimum? Well, x equals 0 is where it occurs. Plug that into our original function. Oh, when x is 0, y is 0. The point is 0, 0 for our local minimum. Incidentally, 0, 0 is also our intercept. So what a coincidence. Part G, concavity and inflection points. Okay, we need to find the second derivative and set it equal to 0 to find candidates for inflection points and to find to determine our intervals of concavity. So this is a big derivative. It takes one product rule and a sum rule overall, and we work it out. We do some nice simplification to get to this step right here. And we're curious about when this thing is equal to 0. Well, again, this is one of two ways. Secant of x is 0, if that's possible, or 1 plus x tangent of x is 0. Well, secant of x, remember that's 1 over cosine. There's no way, there's no x value to plug into that to make it 0. So that can't be a solution. So what we're looking for are solutions to this term, right? This part being equal to 0. So x tangent x equals -1. We'd have to convince ourselves that this doesn't have any roots either. And some checks would be, guessing and checking. If we plug in pi over 4 or negative pi over 4, this is going to be a -1, and we get negative pi over 4 here. So we get positive pi over 4. If we plug in, well, I guess the thing we could argue for ourselves is we can never get a negative number out of x tangent of x. So that's an interesting point to understand, because if x is negative, and we have a negative here, if tangent of that negative number is going to be negative as well, so there's no way we're ever going to get a -1. So it turns out the second derivative has no roots, right? So there are no concavity changes. Now, the last thing we want to know is, well, what concavity does it have? It has only one concavity. Let's plug in a point. Why not 0, right? It needs to be in our interval negative pi over 2 to pi over 2, but it can be any one of those values. So we plug in 0 to this function, and we've got secant squared of 0 is 1, or 1 squared, which is 1, and 2 times that 1 is this, and then times 1 plus 0, this is, again, 1 plus 0 times tangent 0, so 1 plus 0. So 2 times 1, well, or 2 times 1 plus 0, right? So at any rate, this is 2. 2 is greater than 0. The second derivative is positive at 0. So we're concave up on this interval. We're concave up everywhere this function is defined. There are no roots of that second derivative, so there's no concavity change. So when we go to sketch this, we know a few things. We know we have asymptotes here. We've already checked that this one approached infinity as we approached pi over 2 from the left. And by symmetry, we can just fold this thing over and know that it's going to do the same on the left. Or we could have checked the limit as x approaches negative pi over 2 from the right and seen that it also goes to positive infinity. We know the point 0, 0 is on this curve. Not only do we know it's an intercept, but we also know that it's a local minimum. Right? We've already pointed that out. X equals 0, y equals 0. So maybe I add a little bit more detail up above. This is maybe better written as the point 0, 0 is our local minimum. And is there anything else we need to think about with this? Well, we're concave up everywhere. Well, that's good. We have to be concave up in order to draw this shape and not cross those asymptotes. So there we have it. This is the graph of y equals x tangent of x, or at least a sketch of that graph. So those are it. We went from easy to medium to difficult, right? I'd say this is an easy version, the polynomial version of these. I think most of these problems turn out to be the rational function version, which is a medium difficulty. And then these tend to be a little bit harder because solving some of the first derivative equals 0 or the second derivative equals 0 equations can be a little bit more involved and take a little bit more critical thinking instead of just mechanical application of algebraic techniques. There's not really any set in stone way to solve equations like this or to find roots of equations like that. So we have to be a little bit clever about those. Lastly, you'll note that I've got an example here about, this is the mass of a particle from the theory of relativity. And I think I'll just spend 1 second on it. We can get a graph of this curve. Notice that mass is a function of v, the velocity of the particle. M naught is a constant. It's the mass of the particle when it's at rest. And c is the speed of light, which remember is constant in the theory of relativity. And it's interesting that we can evaluate this function. And I run through all the same processes that we did before, only our constants aren't numbers anymore, they're letters. That's fine, we can still do a lot of this. I think that maybe the most interesting thing about this, I'd just like to point out, just for more or less for the fun of it, is the asymptotes involved here. So the function's not defined. Its domain turns out to be between negative c and positive c. And you'll see why, because we're taking the square root of something. This number here, 1 minus v squared, needs to be greater than 0. So when you go to solve for that, right, you have v squared over c squared is less than 1. And then you have v squared is less than c squared. And if you solve for v in this inequality, you get the following. V needs to be greater than negative c, but less than positive c. So it needs to travel whatever direction it's traveling. It's got to have velocity no more than the speed of light, and it's got to have and velocity no more than the speed of light in the opposite direction, right? Negative c. So we know that that's its domain. Now, the curious fact is what happens as we approach that speed of light. So you probably heard, maybe in popular science shows or something like this, where they talk about as an object's velocity increases, so does its mass, right? So let's see what happens when we look down here. So as its velocity increases, well, that's approaching the speed of light in the positive direction from the left, or the speed of light in the negative direction from the right. Well, that's just looking at v approaching c, right? We'll say from the left, so numbers that are less than this. So this is still, these numbers are less than 1, but they're approaching 1 from the left. So that's 1 minus something slightly smaller than 1. So that's approaching 0 from the right. And if we approach 0 from the right here, this m naught is a constant, and the denominator is going to 0 from the right, so we're positive, right? This is also a positive number up here. So that's that meets with our, maybe our popular science understanding of relativity. As your velocity approaches the speed of light, your mass, or your relative mass, approaches infinity. There we have it. And the rest of this follows as we've done before. It's a little messier, it's a little more advanced. It might even be an example in the textbook, so I won't drag you through it in the video here, but it is an interesting analysis. And with all this information together, I'll leave it to the student to get a sketch of this curve, but I believe it should look something like this, wherever that speed of light is, which is a really large number, so it should be way out here, I suppose. So something like that. Anyway. That's it. Curve sketching is just these sets of steps, easy problems with just a lot of work. It might take a little bit to put it together in the end, but that's where the practice will pay off.